All right, so I can do this video in 5 seconds. You ready? An inode is the metadata about a file, not the file contents itself, but the metadata, the size, the owner, the permissions, the metadata. That's what an inode is. There you go, end of video, right? Not quite. There's still more to go over, unfortunately, okay? So let's pull up this meme. I made this meme specifically for this video. I was at the top of this bell curve before I started researching for this video, okay? No, they just store metadata about a file. Why is that hard to understand? That's where I was. People would ask me, Dave, can you demystify inodes for me? Can you explain inodes? I find them very confusing. And it's like, you know, I remember being there. Hey, that's totally fine. It's just metadata about a file. Why is that so difficult? When I started researching and going deep into it, I realized, oh man, these are more confusing and less well-defined than I had realized. So, if you watch this video, I will get you to the top of the bell curve. I already pretty much got you there in the first 5 seconds. We're going to go beyond that. We're going to dive into inodes and explain them specifically on, like, you know, Unix and Linux file systems or whatever. We're gonna dive into them so much that you will leave this video on the right-hand side of this bell curve. You'll be like, okay, they are confusing, but I feel empowered because I understand more about them. They're still confusing, but now I understand why they're confusing. I'm not just confused with no understanding. You'll be confused, but you still have understanding, all right? So hopefully that sounds enticing. All right, so let's jump into it. I got a terminal pulled up here. I am on my Mac system, but this should be no different depending on whatever, like Unix or Linux, like operating system you're on. So I am on Mac specifically for this demo, but it doesn't matter. I could be on any sort of other operating system. I'll even talk about some of the operating system differences here, but for the most part, things are gonna be pretty much the same. So the first thing we can do here is let's go ahead and make a new directory. We're gonna call it empty, and it will be an empty directory. That way we know it's brand new, we go into it, we can do a pwd, that is where I currently am, do an ls, and we can see, hey, it's empty, that's awesome. So let's create a new file. We're gonna echo foo into file.txt. Now we have a brand new file called file.txt. If we cat the file, we can see that we get foo back. That is the contents of the file. That's great that a file has contents, but what else does it have? It has metadata. We have information about the file. We can learn things about this file. We can use the stat command. So if we stat file.txt, we get output like this. You may not be used to output like this. If you're on a Linux system, you will have the GNU variant of stat, which is gstat. So if we run gstat over here, we can see that this output might be something you're more familiar with. Either way, we get information about the file. So as you can see, we have the size of the file, we have the file name here, we have the device ID, the inode number. Hey, that seems relevant here. Wow, we have a whole lot of information. I'm gonna be totally honest, I'm not super used to the GNU version of this. This might be what you're used to if you come from like a Linux-centric universe. Yeah, this is wild to me. But these are both getting information from the same source, which is the inode of the file. Big asterisks around that because we're going to dive into that. But yeah, here's the information that we know about a file. Here's all the metadata. All right, so let me clear the screen so we have a little bit more space to work with. We can stat the file using the mac stat command. We can use gstat on the file to use the GNU stat command. Under the hood, they're both using the same mechanism to get this information. They are using a system call, meaning they are asking the kernel to get information, and the kernel knows how to work with the file system to get this information. So it's pulling this information from the inode and filling up what's called a stat buffer. The reason it's called a stat buffer is because it's using the stat system call. We can do man, two is for system calls, and stat. The reason you need the 2 there is because without it, it will give you the stat. It'll give you the man page for the stat command. Notice the 1 here. 1 is where commands are. The command and the syscall share the name, so we have to manually specify 2 here, which gets us stat2, which is the system call. This is the underlying function. If you were in a C program, you would include this and you would call this, and this is how you actually trap into the kernel to get this information. We say, hey, let's stat this file. Let's give it a file name and a buffer to fill up, and then assuming this is successful, it will fill up that buffer with a bunch of information, which is just like a structure. So there's a whole detailed implementation here, or sorry, detailed documentation here, but as you can see, here's the stat struct, at least here's what it is on my Mac. Here's the information that will be filled up when you stat the file. So you can see the same information that the stat command gave us. We have the device that the inode resides on, the inode's number. Hey, that seems like it's gonna be relevant, right? Number of links, the mode, so that'd be like the permissions, the UID, the GID, that's like who the owner, the group, and the user are, the last access, the modified, the change time. Yeah, there's a whole bunch of stuff. We even have the file size here. And yeah, we get all this information when we stat the file. The cool thing is Other languages have access to this too. This is just a system call, just like opening a file, reading a file, closing a file. They're all system calls too. We can access this in other languages. So here, I'll show you a quick little example. We could pull up, let's say, Python 3, and then you can import OS, and now we have OS, what is it, stat, I think? So OS stat, and then you give it the name of the file. So let's do file.txt. And look at this, we get this stat result object back, and all that same information is there. Again, formatted slightly differently, but if we were to look at st_ino, we get the inode number here, which should line up with the inode number here. Actually, you know what? I think in my terminal I can just search for that. There we go. You can see that inode number shows up everywhere. So you get the same information, but if you're in Python, you would have access to these simply like this. You wouldn't have to fork out to these external tools. You have it built into your language. I think Node also has this, if I remember correctly. You have fs. Yeah, so I think you can do fs.stat, and of course it's asynchronous by default, so let's do stat sync, and then we can do file.txt. And this gives us the same thing. We get this stats like named object. I don't know JavaScript that well, but it's the same information. So we would have the inode number the same as we had it in Python. So pretty neat, pretty cool. All right, so let's recap. What do we have? Let's ls the current directory, which you can see we've already done above, and we have file.txt. So in order to get the file name, we can use ls, and we get the name of the file. That's all we have. We have a string that represents the name of the file. That's it. So we have a file name. That's the first thing. If we stat it, we have the metadata. That's the second thing. And if we cat it, we have the contents of the file. That's the third name. File name, metadata, and contents. Notice that I separated file name and metadata. There's a reason I did that. Because if I stat file.txt, you can see the file name shows up here. So you would think that it's part of the metadata, right? If I gstat file.txt, you can see the file name shows up here. So you would think it's part of the metadata, right? Well, if we use, like, let's say that Python example, Python 3, import os, os.stat file.txt, notice what's missing. There's no file name here. The file name is not stored in the inode. The file name is not part of the file's metadata. This is very important. This is how we have things like hardlinks and basically just hardlinks, and I'm going to talk about symlinks later. That is a source of fear for a lot of people. I know hardlinks can get very confusing. We're going to talk about that. We're going to demystify that in this video. So don't worry, I'm going to break it down. But just understand that right now, the file name is not stored in the file's metadata. A file's metadata does not know what its name is. Where does that name come from? When I ls my current directory, and my current directory is dot, we get the file name. The directory knows the name of the file, and it knows how to get metadata about that file. So what does a directory actually store? It stores the file names and their inode number. You can think of it like a key value store. How it's actually stored is going to differ depending on the actual underlying file system, but you can think of it like a key value store. In fact, I think I can do ls-i, and it gives me the inode number and the name of the file. This is how the directory stores information. Basically, it has the name of the file and the inode number. Super simple, super useful. So the file name is here. This inode number can be used to get metadata about the information, and then this can also be used to get contents of that actual file. The nice thing is, as a programmer, I don't have to worry about that. I don't have to say, hey, let me take this file name, stat it, get the inode information, get where the contents are stored, and go into the contents. No. The kernel abstracts all that for me. I can just call read on an open file descriptor, and bam, I can just start reading the file. I don't have to traverse into it. I don't have to stat it. In fact, when I start reading from a file, I don't actually have the metadata about the file. That's a completely separate call to get that information. So pretty neat, pretty cool. So again, just to recap what we have here, I went ahead and put it up here. There are 3 bits of information. We have the file name, we have the file metadata, the file contents. With the file name, we can get the file metadata. With the file metadata, we can find the offset to where the contents actually start. The nice thing is, like I said, a lot of this stuff is abstracted. So typically with the file name, we can get the contents. You can just call cat on it if you have access to like system commands. If you were in a compiled language, it'd be a little bit different. You have to open the file, and then you'd have something called a file descriptor. That can be a little bit confusing, but long story short, you have, this is your like 3 sources of information around a file, and you can typically use one to jump to the other ones. But again, a little complex. If you have the file metadata and you want to say, hey, what was my file name? We might not know. We might not know, because your file name could be, the file name's ambiguous, and I will get to that. I'll explain that because it can get a little bit gnarly. All right, so I showed it before, but I'll show it a little bit now. We can gstat file.txt, and that's really great. We can see that it is, where does it show it? I'm not used to gstats out, but here it is, regular file. That is the file type. Files have types. So when I say file, I'm using that term abstractly. File is up here, and there are all sorts of concrete versions of files below it. A regular file is one of them. A directory is one of them. A character special device, a block special device, a pipe. There are all different types of files on your file system, file types. A symlink is a type of file. But typically, you mostly deal with regular files, and the other variant you see very commonly, directory. So as you can see over here, this file type is a directory. So it has an inode number. There is metadata associated with the directory. We have permissions associated with the directory. We have access, modify, change, and even birth time. I'm surprised to even see that one there. I didn't know that was a part of it. Typically, I only am used to seeing modify, access, change. Different file systems may or may not actually record when the file was created. You just have access, modify, change. Also, I should probably mention this. A lot of modern operating systems have A time set to off. That means they do not record the access time, because recording access time can be kind of costly. Think about it. Every time I access a file, if I'm like catting a file, I have to go update this timestamp. Every read effectively becomes a write. There's a performance penalty with that. So I see a lot of operating systems actually just turn off A time. So I wouldn't rely on this to be there, but you do have your modify time and you do have your change time. Actually, you know what? I'm going to talk about the timestamps because this is kind of important. Let's gstat file.txt. We have a change, a modify, and an access time. I wouldn't expect birth to always be there. I don't know the rules on that. I typically only see the MAC time. So I'm just going to talk about those three. We can see that they were all modified, access, and changed at the same time. That's pretty cool. That's awesome. Let's go ahead and change. What can we change? Let's change the permissions of this file, okay? So we have it set to 644. Let's change it to 755. Let's make it executable. We're not going to execute this, but we are going to change the permissions of file. So let's go ahead and gstat that again, and let's look at what happens. As you can see, this timestamp was updated. Not modify, not access, just the change timestamp. The change timestamp is modified when you update its inode. That is when the change time is modified. The modify time is changed. Oh, wow, these are terrible names. The modified timestamp is updated when you change the file's contents. The change time is updated when you change the file's inode. So that's kind of how I keep track of those two. But there is some weirdness with that, okay? I'm going to show you what I mean when I say there's weirdness. Let's go ahead and update the contents of the file. You might expect the M time to change, and you're correct. The M time will change. Notice the modified time is now 2159, whereas before it was 2158. But notice what also changed. The C time also changed, which leads me to believe that the inode has changed as well, right? The answer is yes, it has. Because in that inode information, even though we don't see it when we call stat, the inode knows where the contents of the file is. So along with the metadata about the file, we have, the type of file it is, the regular file, we have the permissions, we have the UID, we have the GID. We also keep track of where the contents live, the offset of the beginning of the contents of the data, so we can know where to look for that data. So when you modify the M time, the modified time of a file, you also have to update the inode. So that typically is what happens there. And I know that on some systems, I believe that doing that also will update the access time, even if A time is off. This is file system dependent. I know there's all different types of A time options. There's like A time. I've seen A time set to M time, I believe, where the access time of a file will get updated when the modify time stamp of a file gets modified, so you'll never have a situation where access is below modify, which is kind of nice. But yeah, like I said, I don't even kind of look at this. I just kind of assume if I'm on a system, the A time or the access time is going to be meaningless. That's my general assumption. Okay, so I've been rapid firing information at you for a while. I'm going to slow it down a little bit, and we are going to look at some very concrete examples. We're going to make some files on the file system. We're going to make some directories, and I'm going to go through and illustrate exactly how they're laid out to hopefully kind of demystify some of this for you, because it gets complicated quickly. The file system is incredibly simple to work with, but incredibly complex when you start looking at how everything is wired together. It is a very complex, it is a very simple tree structure, but because everything can sort of link to each other, it can create these complex graphs and complex webs, and there's a lot of terminology that goes with it, where we can take for granted, this is my favorite thing, as a programmer, I can take for granted that it works, but when you actually start looking into how it works, it gets complex quickly. So let's dive in with some concrete examples. Okay, let's take some inventory. Let's see where we are. We're in this directory, this empty directory. We have file.txt. That's great. Let's back out of here. We are now in this directory. We have a bunch of stuff here. I'll go into detail with all this stuff eventually, but for now, let's make a new directory. Let's just call it dirs. We are going to make some directories in this directory. Hey, that's pretty simple. So the first thing we're going to do is we're a programmer, so we're going to zero index it. Dir 0. This is going to be our first example directory that we work with. So it's an empty directory. We are going to keep it that way. If we were to ls it, you can see that there's nothing in this directory. It's completely empty. We could run tree on it and I'll find out that I don't have tree installed. Let me just go ahead and fix that real quick. And with movie magic, we can just edit this out. All right, so if we run tree on that, a command that I've had installed this whole time, we can see that there are 0 directories and 0 files. It is a completely empty directory called dir 0. Hey, that's awesome. Simple enough, right? So let's go ahead and let's make a diagram for it. So we run make diagram, dir 0. We run this, and that image is very large. Let me go ahead and make that a little bit smaller. Image size equals 50%. Run this, and there we go. That is a nice image that explains what's going on in this directory. Let's pause here real quick. You're probably wondering, Dave, what is going on here? You're running some program against a directory and it's making an image that's being output on your terminal? Yes, it's okay. Don't worry. This is a little bash script that I wrote. So if you run file on this, you can see it's a little bash script and it forks out to a Rust command that forks out to a Node.js program. I've written some of the code. I'm using other open source code. I will dive into how all of this works because I know if you're watching this content, you're probably a nerd and you probably want to know exactly what's happening here. I will dive into all that at the end of this video. For now, we are just going to take for granted that this program works and we can output nice diagrams on the terminal, and I will use them to explain what's happening here. So first example, we had a directory that was completely empty. Here is what that directory looks like, and I'm going to teach you how to read this graph. This is a little design that I came up with. And so the first thing we have here is ls dir 0. This is just so we know what the name of the directory is that we're LSing. When you ls this, you get a list of all the files in it. And what files are in it? Well, there's nothing. They're completely empty. So that's why this section here is completely empty. Down here, this is how you would get this information. You would either call the command ls, you can see the backticks around it. You would call the command ls, or if you were in C, you would call read dir. This would be like a system call, but I think on modern systems, it's actually a C standard library call that calls other syscalls under the hood. Long story short, you would either use the read dir function. So in your programming language, you would probably have something like this, or you would use the ls command to get this information. What information you get? You get the list of files there, which as you can see, there's nothing, it's empty. And this right here, this is the unique identifier for it that I've come up with for my diagram, but these two numbers are key. This is the device number underscore the inode number. So let me show you. Let me stat dir 0, and we can see that we have the device number here, and we have the inode number here. With these two numbers, we have a unique way of representing this file on my entire computer. The inode number is unique for the file system. The device number will reference the specific device, or in this case, like the actual file system. So different file systems will have different device numbers. That way, if you combine these two numbers, this is unique for my entire system, and that's how I'm generating this number at the top. So you can get this if you stat it. This is the device number. This is the inode number. If you run gstat, you can get the same information. So you can see that we have an inode number here, and we have a device number of this. Well, it actually is the same. Pretty confusing, but it gives it to you in major and minor format. I'll be totally honest, I'm used to seeing it in this format where it's just one big 32-bit integer, but I've also seen it like this. I know gstat kind of prefers it where you have a major and a minor. As far as I can tell, it seems like this is the first 8 bits and this is the rest of the 24 bits. So you could take this number and shift it by 24 and add this number to it. So if you wanted to get this information or translate between the two, you could do something like, I'm gonna be doing math off the top of my head, so this could break. I think you can do like 1, which is the number here. So 1 times 1 shifted over 24 bits, and then plus this number over here, which is the minor number, 14. And I think this will work. Did I get this backwards? I might have gotten it backwards. I got it backwards. I always get the shifts backwards. Oh man. So yeah, you can see this number here matches this number here. Very complex math. These are the same number, just expressed differently. if you were to use like whatever programming language like Python or Node or whatever, or even Rust, you pretty much get it like this, the 32-bit integer. GNU-stat just gives it to you in this nice format, but GNU-stat also takes like a format option where I can say, hey, you know what, just give me this as a number. So with those two pieces of information, we get the nice unique identifier for the directory, and as you can see, I'm using that in this diagram. This diagram, again, is just for an empty directory, so kind of boring, so let's go ahead and make something a little more exciting here. All right, so let's make our next directory. We're gonna make dir1, and then we are going to echo hi into dir1 foo.text. So we are going to create one file in that directory. Very simple. If we ls dirs1, you know what? I'm actually getting sick. Let's just cd, sick of doing it this way. Let's cd into dirs, and then let me set up a nice little alias for make diagram real quick. We're going to be super lazy here. Normally I would just make a symlink, but because I want to talk about symlinks in this video, I'm going to go ahead and hold off on that for now. We're just going to cp the make diagram command into here. Not great, duplicating code, don't do it. I'll teach you how to use symlinks and we'll clean this up later. But this way I now have make diagram in here, so I can just say make diagram dir1, and this is a lot easier to run, a lot easier to see. So here we go. If we run tree on dir1, we can see that we have one directory with a file named foo.text. So if we look here, we ls dir1 on the left here, and there is one file in it, foo.text. Foo.text, if you follow it, you can see that its inode data is here. So we have an inode with a device number and an inode number. So again, these two things together gives it a unique identifier. And here's all the information about a file. About this file specifically. It's a regular file. These are the permissions, 644. The UID is 501. The GID is 20. Notice that it doesn't say Dave and staff. You would have to get that information. GNU-stat gets that information for you. In the inode itself, it just has the numeric representation. So we have UID 501, GID 20. The size of the file is 3. That means if we were to cat it, there would be 3 bytes in that file. The number of links to it is 1. We'll talk about links in a second. And if you want this information, you need to call stat or lstat. These are the syscalls. So stat or lstat are the syscalls. So in your C program or any other language, you would do something like that. And stat is the program you would execute. And then if you were to cat the file, you would get the data blocks for foo. I didn't actually put the data blocks in here, but I think foo is, what did we even put in foo? If we cat dir1 foo.text, we get hi. So yeah, so if you were to cat it, you would get the text hi. Notice that there are 3 bytes in there. You're probably thinking, Dave, I only see 2 characters. There's a new line in this file. That's why it didn't show up on the same side of the prompt. So if I were to pipe this something like xxd, you can see hi period. We have hi and then 0a, which is the new line character. So there are 3 bytes in this file. As you can see, the inode stores that information. This is very important. You have to think about this. The inode knows how big the file is. That means if you modify the file, we have to also update the inode. So the file system is responsible for doing this information. And if you've ever done a program like this, you're thinking like, do we have to start locking things? Do we have to do things in the correct order? Can we get into weird situations where we update the content of the file without updating the size of the file or vice versa? The answer to all this is yes, of course. There are a lot of locks in your file system, depending on which file system you're using. And some file systems can get into weird situations where the inode doesn't line up with what actual data is there. Spoiler alert, we kind of go with what the inode says. You might just have some data that's not being referenced or data that gets lost as a result of this. If you've ever been in like, an ext file system that has like a journal or whatever, you know that you might have to run fsck and it will go through and fix some of the stuff or try its best to fix some of this stuff. If you were on ZFS, you're not going to run into these issues because it's a copy on write file system. But yes, this is something that has to be thought of. The nice thing is, as a programmer that just calls ls and stat, I don't think about this stuff. I'm not writing file systems. But if you're dealing with file systems, you got to worry about that stuff. And it's super cool. It's super cool that people have taken the time to do things like that. I think that's awesome. Let's make a slightly more complex example. dir2. What are we going to do here? Let's echo hi into dir2 foo.text, very similar to what we had before. And we'll echo by into dir2 bar.text. Okay, now we just have 2 files, 2 separate files with 2 different pieces of information in them. If I run a tree on them, you can see it looks like that. If I run make diagram on dir2, it will go ahead and make the diagram for us. And this is a lot larger of a diagram. The reason it's larger is because we ls dir2. It has its own inode and device number. That's cool. We have 2 files in here, foo and bar. So foo points to its own inode with its own inode number, with its own file size of 3, and then it points to the data blocks for it. So the data blocks and the inode for that file is separate, which it should be. These are 2 completely separate files with different sizes. They were created separately and they have different inode numbers. Their device numbers are the same because they're on the same file system, but their inode numbers are different. They are two completely unique files. Hey, that's awesome. Why am I stressing this point? That seems very obvious, right? Let's make dir3 and let's see what we can do here. I'm going to cd into dir3 just to show this example. What are we gonna do? We're gonna echo hi into foo.text, which we've done before. So now we just have a simple file in there called foo.text. And now we're gonna create a hard link. We're gonna create a hard link of foo.text and we're gonna call it bar.text. For some reason, there's like a joke online, people talk about this. When they start using the ln command, all their rational processing ability just flies out the window and everyone's like, I can never remember the order to these arguments. So I'm going to teach you a little trick for this, okay? We want to create a hard link of foo.text and call it bar.text. So that's the order we're going to do. Now when we ls, we have two files there. Hey, that's really simple. I'll talk about the specifics later, but to remember the order of arguments, it's surprisingly simple. When I cp file 1 into file 2, this is the source and this is the destination. The destination, or the thing you are creating, the thing that will exist at the end of this command, is at the right, okay? Let's talk about mv. Move file 1 to file 2. The thing that you are creating, the thing that will exist at the end of this command, is file 2, okay? Let's talk about ln. The thing that you are creating, the thing that will exist at the end of this command invocation, is at the right. Source, destination. Let's make a symlink. We just use ln-s. We're not going to make one here, but let's symlink file 1 to file 2. The thing that you are making, the thing that will exist at the end of this command invocation, is at the right. Here is your source and here's your destination. Don't think -s source. No, -n modifies the behavior of ln. This isn't an option to the -s flag. -s is a Boolean flag and file 1 is an operand to the ln command. So the source of the ln command is here, the exact same way the source is here. The -s modifies what type of link it makes. Source on the left, destination on the right. Whatever is on the right should exist at the end of this command invocation. It might already exist, maybe if you're overwriting a file, but at the end of this command, this file should exist if the command was successful. That's how to remember those arguments, okay? So what do we have here? We have created hard links. So what does that mean? If we ls these files, we can see that there's two files here, foo and bar. If we cat foo, we get hi. If we cat bar, we get hi. We get the exact same data on both them. That's pretty awesome. What if we gstat them? Let's gstat both of these files. So here we go. We got bar at the top, foo at the bottom because they're sorted alphabetically. They both have a size of 3. They are both on device 1, 14. And look at the inode number. They both have the same inode number. There is your trick right there. When you see that two files have the same inode file, they are hard linked. They are the same file. They point to the same data. They're not duplicated. If I cat foo and I cat bar, yes, I get the string hi twice, but it's pulling it from the same place on my file system. They are effectively the same file. Now you might be thinking, okay, well, which one came first? Did foo.text come first or bar.text come first? It doesn't matter. They're both the same file. If you're thinking, well, which one's really the file? Like if I delete bar, I'm still okay, but if I delete foo, does bar go away? No. They both point to the same data. This file has 2 links because of the hard link. The previous files had 1. This has 2 links. If you delete one of these, that number of links goes down to 1. If you delete all of the links, it goes to 0, and then it will be cleaned up. You could think of this like garbage collection if that helps you. As long as there is greater than 0 links, then there is something pointing to this file and it won't be cleaned up. So if you're trying to say here, well, which one's the real one? They're all the real one. Don't think about which one came first. It doesn't matter which one came first. They are all equally valid. As long as one link exists, this file exists. If you delete all of them, then it goes away. But there is no real one or not real one. I could rm foo, cat bar, and it's still there. Now I will hard link bar to foo.text, and I will rm bar. If I cat foo, it's still there. Now I will hard link foo to bar.text, and now I have both files there. And if I gstat both of them, even though I deleted both of them at one point, and we do a search for the inode number, it hasn't changed. The inode number is exactly the same. So there is no one real file, okay? When a hard link exists, it means that they point to the same inode. So let me make a diagram for this. Let me make sure I'm in the right place. Cool. Let's make a diagram of dir3. This is in stark contrast to dir2. If you remember dir2, they pointed to separate inodes. In this example, we have two files here. They both point to the same inode. They point to the same inode. They have the same inode number, ls-i dir3. They have, well, let's separate them by new lines. I can just put a 1 here to separate them by new lines. They both have the same inode number. They are effectively the same file, and that one inode points to 1 bit of data blocks for it. So that is what a hard link is, okay? So of course, we mentioned hard links. What's next? Well, obviously, we have symlinks or soft links. We can do the exact same thing we did before. We create directory 4. We have an empty directory here. Let's go ahead and echo hi into foo.txt, and let's create a symlink. So just like we did this before, we're going to run this exact same command, but with a -s. Now when we ls highlights it differently because it knows it's a different type of file. If we ls-l, you can see that it will even point it. It will resolve it for us. There's some magic happening under the hood here. We can do this ourselves. We can use the read link command. I believe this command is POSIX now, but wasn't POSIX in the past. I'd have to double check that, but most systems typically have a read link command, though I wouldn't really rely on this exists, and you really don't need it. You can kind of just treat a symlink like the actual file. But if I run read link on bar.txt, it will give me foo.txt because that is what a symlink points to. Here's the thing about symlinks. These are not the same file. These are absolutely not the same file. I will show you that by gstatting both of them. So as you can see, bar.txt points to foo.txt. This one is a regular file. Foo.txt is a regular file. This is a symbolic link. Just like it was a directory before, this is a different type of file. This is a special type of file. There's only one link. There's only one link. They don't know of each other. Look at this. They have different inode numbers. They have different inodes. They are different files. When you actually go to cat bar.txt, a lot of magic happens there. Your kernel handles this, the file system handles this, all of this gets handled for you. So as the programmer, I don't have to think about this. I can treat it like a regular file, but the kernel has to actually resolve this into, what is it, read link. It has to do this for you, find this name, and then re-look up that name, find it in the directory, get the inode number for it, and go through that whole process here. So symlinks point to a literal string. Symlinks store like a string, a path name of the file to look up. Your kernel handles resolving all that for you. That's awesome. But it has a literal string, its own file that points to a different file that may or may not exist. If I rm foo.txt, bar is still there. If I cat bar, no such file directory, even though bar is still there. It exists, but it is a broken symlink. So I think ls might actually show you this. Oh no, it doesn't. Well, maybe GNU ls does. I don't know, it's been a while. But that symlink exists and it points to something called foo.txt. It doesn't care what it points to. It points to a string. It could literally be any sort of like data in here. It points to this, and then your operating system will then try and find that file. And if that fails, even though bar.txt exists, you get no such file directory because it falls through to the underlying file there. If I were to touch foo.txt and then recap bar.txt, it would work. That's awesome because the symlink suddenly is pointing to something valid. So that's how that works. It's a little bit interesting. Symlinks are nice because they can point anywhere. Hard links are restricted. You can only hard link to a file on the same file system. I can't mount an external drive and then hard link from my hard drive to that external drive. No. It has to have the same device number. It has to be on the same device. Symlinks don't have that rule. They can just point anywhere because they're not pointing to a file, they're pointing to a path. And that path gets resolved when you go to access that symlink. So whether it's broken or not, you don't know until you actually try to access it. So let's see what this looks like. So make diagram on dir4. Let's go ahead and run that and see what happens here. So we get pretty much the same thing as when we had two separate files. We have two files here. They both point to two completely different inodes, which is super interesting. Notice this inode down here. See how it says symbolic link? That's because we know this inode is a symbolic link. Here's something interesting. We have two functions down here, stat and lstat. If I were to use the stat function, we wouldn't see that this is a symbolic link. It would think that this is a regular file. We need lstat, which says, hey, give me the information, give me the inode information about this file, but don't follow symlinks. Don't treat symlinks as special. Treat symlinks like their own file type. So I'll show you. Man to stat, and let's go down here. The stat function obtains information about the file pointed to by path, blah, 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 blah. The lstat function is like stat, except in the case where the name file is a symbolic link. Lstat returns information about the link, while stat returns information about the file the link references. That's why, even though that seems weird, you might think, why would you ever want one or the other? The beautiful thing is if my program just needs to get like file size, maybe I'm running like a web server and I need to get the content length, so I want to get the file size. I don't need to know if it's a symlink or not. I don't need to care if it's a symlink or not. I just want to say, hey, what size is this file? If you're a symlink and you point over here, if you're Alice pointing to Bob, pointing to John, I don't care. Just tell me what John's file size is. Weird analogy. I don't know why I use names and files. My point is, stat is when you don't care that it's a symlink and you just want it to fall through to wherever it resolves to. Lstat is when you say, hey, I actually care if you're a symlink or not. So for my program here that generates this diagram, I care. So I'm calling lstat under the hood because I care that it's a symbolic link. Because we know it's a symbolic link, we can see that the target of this link is foo.text, a literal string of foo.text. You can get this information using readlink. That's the command or the function you would call. So once it sees foo.text, it goes all the way back to this directory, resolves foo.text, points here, points here. That's how that works. All right, so let's make a new directory here so we can talk about something else with symlinks, because symlinks are very interesting. So we're going to go into dir5 here. We have an empty directory. We're going to do pretty much exactly the same as we did before. We're going to create foo.text. Now we're going to create a symlink of foo.text because that's the source, and bar.text, that's the file we want to exist after this command runs. We run this. Hey, that looks good. Now we want to say, let's make the source bar.text, which in itself is a symlink, and we're going to call that baz.text. So let's go ahead and do a long listing on this. We have a regular file named foo.text. We have a file named bar.text, which points to foo.text. And we have a file named baz.text, which points to bar.text. So as you can see, we have a single level of indirection. If we cat foo, we get high. If we cat bar, we should fall through to foo, and we get high. If we cat baz.text, we should fall through to bar, which will then fall through to foo, right? Yeah. Exactly. That's all it does. There's no trickery here. It works exactly the same as what we've been talking about. You can point as many symlinks as you want to each other. Asterisk next to that. There is a limit you can hit. But long story short, these are three separate files. They have separate inode numbers, but when you call readlink on them, you can see that, well, that's a bad example. It doesn't show which file I actually called readlink on. But yeah, it's easier just to do ls-l to see it. You can see that two of these are symlinks. They point to that. So there's going to be three separate files with three different file names in here. That's awesome. Let's go ahead and make a diagram of that. What did I call it? dir5. So let's go ahead and run make diagram on dir5. And we can see that we have to scroll a little bit for this diagram. But look, we have three files in here. Baz points to its own inode, which when you call readlink on it gives you bar. Bar at the bottom here points to its own inode that when you call readlink on it gives you foo. And foo, when you get its inode information, it's its own inode. You can't call readlink on it. Well, you can, it'd just be an error. You can call cat and just get the file contents directly. Obviously, the nice thing about symlinks is I can just call cat on them too, and it'll get resolved for me. But if you're actually looking at the structures here, there are three separate inodes here. You can stat these files and get the same inode information. If you were to use the stats as call, it would all resolve to this one right here. But if you use lstat will give you this inode down here or this inode up here because they reference the symlink itself. Hopefully that makes sense. Okay, so remember when I mentioned there actually is a limit here? I'm going to show you a pretty easy way to hit this limit, okay? So we have no files in here. Let's go ahead and make some symlinks, even though we don't have files in here. Let's make a symlink called, or let's make the source foo and the symlink we are going to create called bar. So now we have a file called bar, and if we do a long listing, we can see it points to foo. That makes sense. Let's do the opposite. Let's make one that bar is the source. That's a confusing way to say it. What I mean is the destination of the ln command will be that foo exists. Foo will get created, and it will point to bar. And now we have a circular, nice little loop of symlinks. So we have a circular symlink here. Foo will resolve here, bar will resolve here. That's not great. If we call gstat on them, it's going to be fine. The reason it's going to be fine is because it's using lstat. It's actually looking at the symlink data itself. That's really great. But what about if we were to cat one of these files? If I cat foo, it should fall through to bar should fall through to foo should fall through to bar, and what happens? Too many levels of symbolic links. we actually get an error specifically for that. Isn't that crazy? So let me do a man on, I don't want a man cat. I want to do man to, let's do open. So this is the system call to open a file. Typically a program like cat would do this to open and read a file. So let's go here. This is how you open a file, and let's scroll down to the bottom. Here are the possible errors that can happen when you, oh my God, there's a lot. Here are the errors that can happen when you try to open a file and something's wrong. I'm going to cheat. I know which error we're looking for right here. E-loop. Too many symbolic links are encountered in translating the path name. This is taken to be indicative of looping symbolic link, of a looping symbolic link. Notice this phrasing. This is very important. Too many symbolic links are encountered in translating the path name. That's perfectly stated. This is taken to be indicative of a looping symbolic link. So the error name is e-loop. E-loop in our case makes sense because we do have looping symbolic links, but they technically don't need a loop. They just needs to be too many of them. So if I were to make a directory of 8 million symlinks all pointing to one file exactly, we'd probably never get to that file. You would get e-loop, and it's basically saying hey, you probably have a loop here. There's too many of them. So it's taken to be indicative. It's not guaranteed to be a loop, but at this point, if you're in this situation, you already have too many symlinks. You should rethink your design. But an easy way to hit that is just to loop them. If you loop them, you're going to get this error. You get this error pretty quick, which is nice. So what does a diagram look like of this? Make a diagram of dir6, and let's see what we get. Very simple. If you were thinking, oh, they're all going to be connected to each other. No, they're not connected because, again, foo, this file here, is an inode. That inode, when you actually look at the contents of it, it's the path name that the link resolves to. So it resolves, just find a bar. We go back here. We find bar. We go to its inode. We call read link on it. We get foo. We go here. We get its inode. We call read link on it. We call bar. We go here. It will create a loop. The inodes, or the symlinks itself are fine. One symlink just resolves to one path name. There's no problem with that. You can have circular symlinks on your file system. It's at the time of trying to resolve them that the problem creeps up. They just sit there waiting to blow up, but then we get e-loop when we actually try to resolve them. If we never try to resolve them, if we just call gstat on them, was it dir6? It's totally fine. Totally fine. We're not trying to resolve either one of them. It's once we start actually going into them that we encounter the problem. Think of it like a program that has a bug in it. If the program's just sitting on your computer not running, it's not really doing anything wrong. It's only when you execute the program that you exercise the bug. It's only when we resolve them that we exercise the e-loop error message. So let's go ahead and let's make another one. Make dir7. So what's going on here? We're not going to talk about symlinks. We're going to talk about something a little bit different. So we're in directory 7. There's nothing here. Make dir subdir. Subdirectories. So now we have a directory with a subdirectory. If we call tree on it, it looks like this. dir7 has a subdir. The subdir has nothing in it. If we were to make a diagram of dir7, get ready for this. We ls it. You can see that subdir points to an inode. This is the inode information about it. Look at the type. It's a directory. It has its own inode number. It's a unique inode, but it's a directory. It has its own permissions. It has 2 links to it. And inside it, if we call ls on it, we get nothing. Now this is interesting. Why does it have 2 links? Because remember the thing that had 2 links before was a hard link. Most files just have 1 link to them. The link tells us how many directories have entries pointing to the inode. Because remember, look at it right here. Subdir points to this inode. That is 1 link. So where's the second link coming from? Because this directory has 2. We will get back to this because I'm going to show you a little bit more complicated example first, but keep that in mind. Notice that this directory seems to have a higher link count than normal files. When we hard linked 2 files together, we had 2 links. That made sense. We had a file and a hard link, so we had 2 files, 2 links. Hey, that checks out. This is a little bit weird, but yeah, keep this in mind. We'll come back to it. Let's move on to the final directory, dir8. So now we have dir8. I'm just going to move into it to make my life a little bit easier. Once we're here, we can touch foo.txt. So now we have a file named foo.txt. Make dir subdir touch subdir foo.txt. It's interesting. The files have the same names, right? I'm going to be a little pedantic here. They don't have the same name. One of them has the name. I'll actually print out its name so you can see it. Here's the name of one of the files. And here's the name of the other file. They don't have the same name. They have unique names. They have the same base name. So these files have the same base name, but they don't have the same exact name. So they're different files. They will have different inodes. One just exists inside a subdirectory. If we call, actually, let me do a tree first. If we do tree on dir, what do I call it, dir 9? That's not right. Dir 8. There we go. So let's do a make diagram on dir 8. This is hard to read. I understand this is hard to read because the subdirectories kind of get a little bit wonky here. Here's what I'm going to do. We've been viewing them from left to right. If you're used to seeing your directories in a GUI fashion, like seeing folders on like Finder or some sort of like file explorer or something like this, left to right probably makes sense to you. But if you're more Unix brain or used to seeing things in a terminal and we go, up one directory, you might be thinking of a tree structure that goes down. So let me go ahead and do that. Let's set direction to TB, top bottom, because right now it defaults to LR. This is a program I wrote. Again, I'll talk about this at the end of the video. Let's do TB. It'll be the exact same thing, but now it will flow from the top down. So we can scroll down and actually talk about it. So the first thing we do is we ls the directory, and we can see that there's a subdir and there's foo.txt. So foo.txt points to this inode, and this inode points to the data for it. That makes perfect sense. It's a regular file, has an inode number of 9936. That's what it ends in. Subdir also has an inode. It's a directory, but of course it has an inode, and we can call ls on subdir, and inside there is a file named foo.txt. So if you follow that foo.txt, we have inode 9939. Look up here, we had 9936. They are different files. Like I said, they are different files. They have the same base name, but they are different files. So this is a way of just sort of viewing those files, and you can see kind of like this is recursive. Once we start having files inside folders, I'm gonna use my terminology correctly here. Once we have directories inside directories, you can see that it will just keep going down another level, another level, another level. Things can get very complicated very quickly. In fact, I should stop right here. If you're only used to viewing things from like a file explorer or something like this, here's how my brain works. When I see a GUI, like a Finder or a file explorer, something like that, I call them folders. They look like folders. That's how I think of them. When I'm in the terminal, I call them directories. I'm talking about the same thing. The reason I call them directories is because it's like a directory, like a phone book, like a Rolodex. Am I just aging myself here? It's a directory because you can look up the base name of a file and get its inode number. It is a directory of base names to inode numbers. That's why it's called that. It's a simple directory. Oh, I want to find out where the file dir6 lives. I want to find out where its metadata is. Let me pull up the directory. Let me find dir6 and hit the string dir6. And hey, it's at 679599552. This is a phone book. I pulled up its phone number. With this, I can get information about it. That's kind of what's going on here. That's how I think of it. So yeah, there was the diagram for directory 8. And we have a nice little top to bottom flow so you can actually see it. This is how it works. So what's next? There's a little more that I want to show you because I didn't lie to you. I gave you a little bit of warning this would be happening. Where did it happen? It happened in directory 6, I think. That's not right. Maybe it was directory 7. Let me just, I should have written this down. Yeah, so directory 7, you can see number of links here is 2. Even though we only see one arrow pointing to it, there's only one link as far as we can see. That's because there are 2 files here that I did not talk about. There are 2 hidden files here that always exist. We have subdirectory inside dir7, right? If I ls dir7, we see that there's a subdirectory there. Are there other files there? Of course, there are 2 other files. We can use ls-a to get all of the listings. There's dot and there's dot dot. These are files that are created. They're directories. They get created when you create a new directory. Your file system handles this for you. You don't have to think about it, and they will exist in every directory. So dot points to your current directory. You have probably seen this if you've gone to execute a script like my script. / just means the current directory. That's all it means. You could do like pwd and it would be effectively the same. Of course, you'd want to quote your expansions, but you could do this and it's effectively the same as calling that. But dot is the name of a directory, and that directory is your current directory. I can gstat dot, and there we go. That's the name of my current directory. I can gstat dot dot, and that's the directory that's one above me. So in this example, dot is your current directory, dot dot is the directory that's one above where you are. So with that being said, look at subdir here. Subdir has 2 links. Of course it has 2 links. It's being pointed to by the name subdir in its parent directory, but it also points to itself. If I ls-la dir7/subdir, it has dot and dot dot. So dot points to itself. Dot is linked to itself. So these directories are hard linked to each other. That's kind of crazy. Let me allow that to sink in. So if I gstat dir7 subdir, that's awesome. I get this inode, 9845. That's what it ends in. If I do subdir dot slash dot slash dot slash dot slash dot slash, doesn't matter how many I do, I will get the same inode number because it is the same file. Dot will point to itself. So these directories can have hard links. They are created automatically for you. And if you're thinking, oh God, I can have hard links with directories, that's kind of gnarly. Can I get myself into really bad situations? Yes, you would be able to if it were possible for you to do that. But if I want to say, let's make a hard link directory, the source will be dir0 and I'll make dir9 here. Guess what? Can't do it. Can't make hard links in directories. They just decided, nope, that would be too dangerous. We get into some weird circular dependencies, and thank God it get way too complicated. So you, the user, can't do this, but the file system, the kernel, like that will handle it for you. When you make a new directory, 2 directories will get created inside it for you, dot and dot dot. They're kind of meta, they don't really exist, but like they do, they just point to existing inode data. So that explains the link count that we are seeing there. So when we go into dir, nope, that's not where I want to go. Let's go into dir8, do an ls, we have subdir. If we ls-i subdir, we can see it has an inode of 67, blah, 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 blah. Subdir dot also has the same inode number. So these directories have the same inode number. In fact, here's a cool little fun trick you should know about if you're on like any sort of Unix or any sort of operating system with a file system like this, gstat slash. Because when you're in slash, the root directory of your file system, dot and slash dot dot, remember these are 2 separate files, they are the same inode. They are the exact same inode, inode of 2. Inode of 2. There's a lot more links because there's a lot more directories in there, but they have the same inode number. This is the only directory where dot and dot dot will have the same inode number. So this is a kind of a cool way of saying, hey, am I in the root directory right now? Maybe you're trying to break out of a chroot jail or something. You can check the inode number of dot and dot dot. If they're the same, then you're at the root of the file system. So pretty cool little trick, something just to be aware of. As you can see, it gets a little bit complicated once we started talking about hard linking directories, but even with dot and dot dot, things get exponentially more confusing. So I will show you how that works. Let's start with directory 0. If you remind yourself, directory 0 is an empty directory. So let's go ahead and make a diagram of directory 0. It's going to be too big. Remember, I shrunk it last time. So there's a giant diagram. There's nothing in there. Awesome. What if we said show dot? No, show dots, I think is what I called it. Show dots will show just the dot character. It doesn't add dot dot. Those are 2 separate flags I've added because I want to show you how wild it can get. If you show dot, I've added the dot to the directory here, and you can see that dot points to an inode. That is the inode for the directory itself, and that inode points to this directory. So dot self-referential. Dot will always point to itself. By contrast, I could do show dot dots, and this will show the dot dot directory. Now here's the thing, the way I've coded this program, it doesn't show dot dot for the root directory, and the reason I do that is because I'd have to traverse up the whole thing and it would just be too much. So in this example, it's kind of meaningless, but in my future examples like the directory 7 and 8 where I had subdirectories, it makes more sense. So let's show that. Let's make a diagram of directory 7 without dot or dot dot, and as you can see, we just have a single subdirectory with nothing in it. So if we did like a tree on dir7, this is what it is. It just has a directory called subdir with nothing in it. So if we do this, but we show dots, now things get exponentially more complicated. Actually, this one's pretty simple. So in this directory, we have dot and we have subdir. Dot points to an inode, and that inode points to this. Remember, dot is always self-referential. Subdir points to an inode, and that inode points to this data, which has dot, which points back to this subdir because dot is always self-referential. So that's what it looks like when you add dots. Let's go ahead, and instead of dot, let's add dot dots. And let's run this here. A little bit more confusing, might be harder to read. In fact, you know what? I'm going to go ahead and let's do a direction TB again. Let's do top to bottom and see if that makes it any easier to read. This is somehow worse. Let's go back to that first one. A little bit small, I apologize for it. But here's the main directory. As you can see, there's a dot dot entry. So dot dot, if you were to follow it, in this root directory doesn't point anywhere, because remember I said I'd make it so the root directory doesn't point anywhere in this diagram, otherwise the diagram would just infinitely recurse. Subdir points to an inode, which comes over here and points to this directory listing, which has ... in it. ... points to the inode, which was the original directory. So ... references the directory above it. ... references the current directory. Of course, you can do show ... and show ... at the same time, and you run this, and a simple example like that suddenly gets very complex. This is why I left it out at the beginning of the video. I didn't want to overwhelm people, because you can see, okay, let's look at the root. We have the root here with ... and subdir. ... points to this inode, which points to itself. Subdir points to here, which points back to here, which points back to here. All right, so notice down here, this subdirectory has nlink of 2. You can see there's 2 arrows coming into it. ... points to itself and subdir points to it. So this directory has a thing called subdir that points to that inode. That's 1 link. And then ... points to itself. That's 2 links. Hey, that makes sense. This one has 3 links. The root one has 3 links. Even though we only see 2 arrows coming into it, that's because I didn't diagram the third link. The third link we have, of course, is we have ... points to it, which is self-referential. We have the ... of subdirectory. So if you traverse into subdirectory to go back up 1 level, it's this inode. And then the parent directory of this directory also points to this one. So there's your third link there. So yeah, you end up having hard linked directories, but you as a user of the file system, you're not hard linking directories yourself. And thank God, because look how complicated this stuff gets. Let's go ahead and show directory 8. Remember directory 8? It's going to get a little bit wild here. A lot going on. I'll show you directory 8 in case you don't remember. We have foo.txt in there, and then we also have a subdirectory which has foo.txt there. So if we go up here, we can see that here is our main directory, the root. We have subdir, foo, ... and ... of course, is simply self-referential. Subdir points to here, which points to here, which foo points to here, and then goes to here. And then we have a different foo.txt. Even though they both look the same, they have different inode numbers. I'm not going to dive into the specifics of this. Feel free to run this on your own time. It's actually kind of a cool tool, and I'll show it off at the end of the video. Of course, if you've made it this far, you know that I could also just run this on ... So if I have this, I could totally just run this, and let's see what it looks like, because I'm actually afraid. There we go. So it'll generate this for you. You're not going to be able to read it on this screen. I can't blow it up enough. But if I were to zoom in, you could actually just, like, technically speaking, you might be able to do this on your whole file system. Don't quote me on that. You probably don't want to run this against the root of your file system. I think the way I handled it might blow up recursively either way, but it is possible to view it like this. Like, there's the root and it points to all these different inodes. So if you wanted to visualize your file system like this, if you were in Jurassic Park and you're like, this is a Unix system, I know this, like, go ahead, feel free, knock yourself out. So let's recap what we have. Inodes have metadata about your files. And that inode information is everything except the file name, because remember, file names just link to inodes. The file name could be anything, and you could have hard links, so that's multiple file names pointing to the same inode. The inode has the metadata, and it also knows where the content lives. It's not the content itself, it just points you to the content. In the case of a directory, that points you to a list of file names and inodes. In the case of a symlink, that content is the path that is the resolution of the symlink. In the case of a regular file, that's just data. That's just data you read. So when you cat the file, you get to see that stuff. So that is how that works. The reason I said it's confusing is because in my brain, the inode information was always the metadata. Simple as that. Inode was the metadata. When I started looking into it further, I realized that inodes aren't as well defined as I thought they were. I thought they'd be in the POSIX specification. They're not. There is something called the INO number, the file serial number. That's the unique number, the number that we see that I call the inode number. But POSIX doesn't specify inodes. The more I looked into it, it seems like inodes are actually the file system that has its own concept of inode. So ext, xfs, zfs, they'll all have their own notions of it. In fact, zfs doesn't even have inodes. It has dnodes, which play the role of what an inode does, plus a little bit more. But the waters are muddied, because if you go in the ZFS source code, it references the word inode. If you grep for inode, it will come up. So if someone were to come up to me and say, Dave, if you stat the file, you get its inode information, I'd be like, yeah, I know what you mean. That's true. That's how I would think of it. But if someone were to also be like, well, I don't know if that's true. The inode is the on-disk representation of that data, and when you stat the file, you actually get a stat buffer, and that stat buffer is built up with information from the inode. I'm doing the nerd voice right now, but I mean, I could see myself saying this, not in a got you sort of a way, just in a, it's surprisingly complex. inodes are surprisingly complex. They're deceptively simple, I think is a way of putting it better. So yeah, if you made it this far, you are totally a nerd. Go ahead and hit subscribe. Take a look. Look at this. There's my YouTube analytics. We can see at the time of this recording, I have 48,000 subscribers trying to hit 100K. So that'd be awesome if you go ahead and hit subscribe. And I think there's one last thing to do at the end of the video, because if you stuck around this long, you probably want to know what's going on with that make diagram script, right? So I'll jump into it. I'll show you. Let's go ahead and be good about this. Let's rm make diagram. And the reason we're doing that is because we know that I CP'd it from here. So let's vim make diagram and actually talk about it. Quick and dirty script to generate a mermaid doc, render it, and display it. So how I'm doing this is I'm using a language called mermaid, which is actually really cool. You draw diagram, you generate text, which then you can turn into a diagram. So that's what I'm doing here. I am running a Rust program that I wrote to take a directory and generate a mermaid document that describes all the inodes and files in it. From there, I am piping that information into MMDC. So as you can see up here, I kind of go into the details of how to get these different tools. MMDC is the mermaid CLI. It's like a node program that will actually take a mermaid document over standard input, because I have -i hyphen here, and generate a PNG file. It can also generate like an SVG and stuff. So I generate a PNG file. I store it here by default, graph.png. And then I render it using ImageCat, which shows an image on my terminal. I'm using iTerm2 on my Mac. So there's a whole protocol for displaying images on your terminal, which is pretty sick. It's pretty awesome. So basically it's a Rust program I wrote, piping into MMDC, which I did not write, which renders this diagram as a PNG. And then we're piping it to ImageCat, which again, I did not write this, but it's a nice open source software, which renders the image on my terminal. So I can specify things like image size, because as you saw in the beginning, generating a diagram for an empty directory was very large. So we can jump into here. Inode Visualizer is the name of the program I wrote. Simple Rust program. If we look at it, it's one file, source main. Convert a directory to a mermaid diagram. So there's a whole bunch of stuff here. We take the direction that was like top to bottom. These are the arguments right here. If we want to show dots, if we want to show dots, and then we also take the path name as the argument. So if I'm an Inode Visualizer, I can do cargo, run, and then I can say the directory I want to do. So let's do the source directory. And this will spit out a mermaid document that will reference the source directory. So as you can see, we spit out an inode for the file that it found. The file that it found was main.rs. And then we emit a class for main.rs. And then we hook up all the lines that you've seen. So the inode data points to the data. The directory points to this. Then we do all this. I don't do any validation. If you have weird file names in here, it will break. I wrote this tool for educational purposes. If you start putting colons and new lines in your file names, oh man, I don't do any sort of safety checking on that. Just letting you know. But yeah, long story short, I wrote this program goes through and does all of it. Let me pull up the main. Here we go. Here's the main method. We set the current directory to whatever you give us. So we CD there, we emit the mermaid header, and then we process the directory recursively. So we start with dot, that's the current directory. And then we call process dir, recursively process a real directory, no symlink following. So then we check, do we want dot dot? Do we want dot? Then we do nice little read dir on it. I won't go into detail of all this stuff. It's very, very simple. I am just emitting mermaid data to standard out, doing no validation on it. But when you get this nice little diagram like this, you could pipe that to mmdc-i-o foo.png, and then we can call ImageCat on foo.png. And it's very small, but it's a simple version of that. I think I specify like the size and all that stuff. So that's how that works. It's super simple. If you're interested in this, all of this code will be open source under the MIT license, and I will make it available at the end of this video. And here is the real end of the video, because now I realized, oh man, my notes were a little bit out of my notes were a little bit out of sync. I transferred the wrong notes to the wrong file, so I completely skipped this part of the video where I write a C program to stat a file that's been deleted, because I show that you can actually have a file that has 0 links. Okay, I'll just run through this real quick. If you made it this far, you're one of my super fans. Thank you so much. You're probably already subscribed. So this is the secret end of the video for you guys. Open a temporary file. We make a file called this file will be deleted. We open it as read only with create, so it will get created. We do our proper error checking. We open the file. We unlink the file, which is deleting the file, but we still have it open, so we can call fstat. Remember how there was stat and lstat? we have fstat. Fstat takes a file descriptor, so a file that's already been opened. We don't need a path in the file system. It doesn't have a path in the file system. We fstat the file descriptor, and then we print the information about it. We then close the file descriptor. You don't have to do this. The program exits right after. But the cool thing about this is if I run make here, and then I stat that file, we can see that we open this file, we remove the file, we have a file descriptor of 3 because 0 is standard in, 1 is standard out, 2 is standard error, so 3 was the next available one. And we can see this file has n links of 0. So it is possible to have a file with 0 links. This will get cleaned up once the process is done. But you can imagine a situation, if you're like me and you've worked like DevOps roles or SRE, sysadmin stuff, you can imagine a situation where this process never exits. Maybe this is a web server that's writing to a log file. The log file gets deleted, but it's still open in this process. So your file system is complaining it's running out of space, but when you run du and look through, you don't see it. It doesn't show up because it's not referenced on the file system, but it's still there. Yeah, you can have these open file descriptors taking up space, and you know, if you're on Linux, you have to start spelunking in the proc directory. It's a mess. This is how you would do that behavior. So sorry this didn't make it into the video, but if you made it this far, hey, thanks, appreciate it. Yeah, you guys are awesome. And yeah, that's all I got. See ya. I wasn't sure if I was going to close the video, but you could do some wild stuff here, because with Node, you can actually give it a -P to print directly to the screen and E to execute JavaScript that you give it. So I could do something like fs.stat_sync, and then I could say, what is it, file.text. So you could do this if you wanted to, run it, and then it stats that file. The cool thing here is instead of hard coding the screen or the string, we could say process.argv1. This would be the first argument that we give it. So if we go over here and give it an argument, file.text, we could stat that file. We could give it the name of the directory that we're currently in, because you can stat directories too. Directories are files just like regular files are. Slight differences, of course, they're not exactly like regular files, but you can stat them. They also have an inode which has metadata about it, which is pretty neat. And then if you didn't like that output, you could do something like json.stringify. Oh man, am I going to leave this in the video? I have no idea. This seems like a little bit excessive. So now we have a stringified version, and then we can pipe that to JQ, and now we have the stat information as JSON, which is pretty neat. So we can wrap all this in an alias. Let's call this nstat for node stat. Put this in single quotes, get rid of the argument, close that single quote here. I'm probably going to put this at the end of the video. So now if we call nstat, we can give it file.text here. And now we have this nice little stat function that uses node that gives us JSON back, and you can get the exact same information. Yeah, this is so much. This doesn't have a place right at the beginning of the video. I'll put this towards the end of the video. Hopefully people will enjoy this. If you're sticking around to the end of the video, I think you're the kind of person who's going to like this stuff. So yeah, look forward to this.